now we are going to talk about, well, I would say seeking balance in realistic ocean flows. So Marcel has already done a very good job in talking about slow manifolds, their invariance, and what we want to achieve with these balancing methods is to achieve wave vortex decomposition or wave eddies or slow and fast manifold, whatever you want to call it, in oceanic flows in realistic scenarios. We have methods which we can apply in idealized scenarios in a configuration where you don't have boundaries and no change in Coriolis parameter. That's not what we want, right? We want to be able to apply it in realistic scenarios and maybe also someday, maybe in observational data. So that's the idea here, and that's what we want to talk about. Marcel has already explained what is balance, the meaning of balance. So I'm not going to talk about that in detail, but just this picture, to show you this picture here. You see this, okay. Okay. No. Okay, but you see these large circular features here, which are quite stable, and this evolves slowly. So these are the balance flows, slowly evolving balance flows. And you see these smaller deviations around it, smaller perturbations. This is related to the wave field or the unbalanced flows. So this also, Marcel has already showed this example here with the atmospheric configuration. This is an idealized simulation in the atmosphere. On the top, you have horizontal velocity divergence, which is an indication of generation of wave or unbalanced field. And below you have actually geopotential. So this is actually indicating the sites where these waves are generated. So this meandering of the flow that you can see there. Then we also have simulations from the ocean model. So this is a 1/10 degree ocean model, realistic ocean model. And a snapshot is from the Gulf Stream, shown as high pass filtered vertical velocity with pressure contours. And again, you can see these wave trains in pink and green, which is an indication of generation of internal waves at these sites where, especially in Gulf Stream, where there's a lot of eddies. We also see some wave trains often in numerical simulations. So you have these red and blue here, which is also indicating unbalanced flows. So the question is, these appear to be generated by balanced flows, but what exactly they are and how much of this is actually unbalanced? And why is it important? It's important because it acts as a sink of eddy energy and at the same time a source of wave energy. So for the energy budget, these two components are important. But again, the question is what they are and how much of this is balanced or unbalanced. And for that, we have flow decomposition methods. We have been working on two within this project. One was optimal balance, which Marcel has already explained very nicely. And the other one is higher order decomposition in Rossby number. So I'm just going to talk about that very briefly. So the method is based on, or it's called nonlinear normal mode initialization. It's based on pioneering works of Mackenhauer and Bayer and Trippier, which was originally designed for numerical weather prediction. And it can be extended to higher orders in Rossby number, and that's the method by one. So we will actually show the extension to four orders in Rossby number. And this is an example to show how we arrive there. And this is an example from single layer model, but we have done this also for primitive equation model in a full 3D model. Okay, so we have here, the pointer doesn't work. But you have on top the equations that you would have for U and H for a single layer model. And if you go to Fourier space, you get a formulation where you have on the left side the state vector Z. This contains your state variables. So in this case, it would be U and H. And then you have the matrix A, which contains all the linear terms, and the vector N, which contains the nonlinear terms. And you notice the parameter Rossby number on the right-hand side, and this is used for expansion in Rossby numbers. So for linear decomposition, if you have the matrix A, you can just solve it for its eigenvalues, and you get 3 eigenvalues. So irrespective of whether you do it for single layer model or a shallow order model or primitive equation model, you will get 3 eigenvalues. The one that's related to 0 is the balance mode or balance motion related to the balanced motion. And the other 2 are related to gravity waves, which are counter-propagating because of the sign. From the eigenvalues, you can get to the eigenvectors. So you have the left and right eigenvectors, which you can use to create a projection matrix. So you can project then your states related to balanced and unbalanced mode onto the state vector. So this is shown below at the projection where you project the state to the state vector Z. I just want to mention here that this is non-trivial. So if you have to do this properly on a numerical grid, you have to do it with the right operators. I will show you an example later why when it becomes important. So once you have projected your balanced and unbalanced mode on the state vector, you can get the two components. And so this is the modal decomposition. And talking about higher orders in Rossby number, so apart from a balanced mode and an unbalanced mode, there's also a slaved mode, which shows up with the unbalanced mode, but it's tied to the balanced mode. And it's important that this is extracted from the unbalanced mode in order to have a pure or as good unbalanced signal as you can get. So this is shown here on the top, actually, where the idea is to use two time scales, a slow and a fast time scale, and then your balanced field only evolves with a slow time scale, whereas your unbalanced field evolves both with a slow and a fast time scale. This might look a bit intimidating, so maybe I don't go in detail now, but I'm happy to talk about it in detail later. But the idea is that you can solve this by iteration, and for each iteration, for each order, you can eliminate slave modes from the unbalanced mode. So you get more and more balanced state and more unbalanced state. Important here to note is that the first order, the first order that you get here is similar to quasi-geostrophic balanced state. I think Silvano will also mention this in his part later. And this is an example to show how this decomposition works. So you have on the right-hand side, the full state, which contains everything. So your balanced flow, balanced field and the unbalanced field. And you can see in between, you have the geostrophic or the slow mode, and on the right, you have the fast mode. So you can see how fast the scales are. And you can also see that the geostrophic component of the slow mode has a large part retained from the full state. So now we talked about we know about the high order decomposition and optimal balance, and now we actually want to compare them because we want to know if the balance is independent of a numerical scheme or not. Okay, so just on the top is the notation. So Z is the state vector, R is Rossby number, and P dot Z is just the linear projection on the geostrophic mode. So that's the linear balanced state. And when you use a balancing method B on this linear mode, then you get a nonlinear balanced state. So in principle, your total balanced state consists of the linear balanced part and the nonlinear balanced part. And how you derive the linear balanced part is straightforward, which I just showed. But the whole game is about how you get to the nonlinear balanced part. And this is the difference in these two methods. So the highlighted in blue and orange are the nonlinear balanced states that you get from high order decompositions, that's the MB method, and optimal balance method, that's OB. Right, so then we compare them. And how do we compare them? So we need a model with exactly the same states in the beginning, and we initialize them with balanced states from each of these methods. Then you integrate it for some time. And then you again, because the flow has evolved and there are nonlinear interactions between the balanced and the unbalanced state, so your balanced state is no longer balanced. And so you rebalance it with these methods, and then you diagnose the imbalance. So just a note here, we have tried to do different model versions, find a difference in spectral code with different parameterizations of including friction and mixing, different time stepping methods, and also do different configurations with initial conditions. So there's jet-like and random. So you see below here on top is a jet-like state, and then after evolution, you have the balanced state. This is from optimal balance method, and below you have the random state and an evolved state, which is then balanced. All right, so how do we diagnose the imbalance? It's calculated as the difference between the evolved state and the full state, and that's give you imbalance or the norm of the imbalance field. So that's the evolved state and the rebalanced state, the difference of that. And I show you below the very right-hand side the diagnosed imbalance for both the jet-like and random cases, and you see that the order of magnitude is much, much smaller than you have for the initial and the balanced state, meaning that there's hardly any wave emission from spontaneous loss of balance in these scenarios. And the highly contradictory invariance low manifolds is somewhat achieved because you have almost no change in the balance state, a very, very small unbalanced state. Just very quickly, how we do this for a range of Rossby numbers and for trying different, both the methods. So I think you cannot see very well, but the black line is the one with the higher order decomposition. The blue one is the optimal balance method. And then we do cross balancing. So we take one balance state and put it in the other rebalance state and the other way around. So that's shown in yellow and red. And what we see is all of these methods are comparable. There are differences, but not too much. And they follow the scaling of Rossby or to the power 4 for wave emission. But if you change the grid discretization, so we try to plug in A grid eigenvalues to C grid settings, and you see that it's way off on the top, the green line. So that's not recommended. And I will just shortly summarize my part. The comparison of both the methods is similar. What we have shown is for shallow water model for 2 different numerical setups. But yeah, in optimal balance, if we try different time stepping methods, there's a strong improvement. We have also checked this for 3D, and the results are similar. But the take-home message is that the spontaneous wave emission from balance flow is not significant in the settings. And the notion of balance in numerical models of geophysical flows is really tied to the particular discretization. More details are in this paper, which we have just submitted to JFM. And yeah, the problem is that you have Fourier transform and you cannot apply it to realistic scenarios with boundaries, etc. And this is where we have Silvano, because he will talk about time averaging. So go ahead.
Yes, thank you. Exactly. So now we have these 2 methods, but they only work in models where we don't have any topography. And now the goal is to make them, to modify them and make them possible and make them applicable in realistic oceanaric scenarios. And so yeah, before I start with how we are going to modify it, here's a short recap on how the optimal balance method is working, or more precisely, what we need for the optimal balance and why we can't apply it in realistic ocean models. So first, we need a model that we can iterate backwards and forward in time. And that usually is not a problem in realistic ocean models. We have friction and dissipation, which might be a little problem because we can't iterate backwards for these cases, but we can just switch them off. So these are minor problems. Then we need a scaling parameter so that we can ramp these nonlinear terms, which is also not a problem, it just needs to be programmed. And then the last point is a boundary condition. So we need to find linear and the linear geostrophic and non-geostrophic modes. And this is where the problem is, because we need a Fourier transformation, a spectral analysis to find them. And yeah, this is now what the next part is about, is just to find a way to do this boundary condition without spectral analysis. So yeah, here's a really simple animation. Again, we have the linear shallow water model, and we have a look on the layer thickness and the Gaussian hill at the beginning. And then we calculate with spectral analysis the geostrophic part and the non-geostrophic part. And if we run it in time, we will see that a wave is propagating away from it, and the geostrophic part is staying constant in time in the linear model. And this is the whole point here, that the geostrophic part, if we don't have any beta, so we don't have Rossby waves or other things, it stays constant, and we're going to use that. So yeah, first what we need to do is we need to linearize our system of equations so that we don't have any interaction between the mean flow and waves. Then we need beta to be 0. This is a little bit problematic. And then we estimate the geostrophic component with a simple time average. So this set 0 here is, oh, where's my mouse? Not here, apparently. So that 0 is our estimation for the geostrophic component, and we just calculate it as a time average. So 1 over t times the time integral from t0 for a time period of t of the state z. And we can show that this is converging by just decomposing this z into the true geostrophic component and the true fast wave component. And because beta is 0 and the model is linearized, the geostrophic component is independent of time. So we can actually pull it out of the integral and end with a term that is Z0 plus a term that is of the order of the wave mode divided by the time averaging period, which means that the error scales with 1/t. Having longer and longer time averaging periods means that we get closer and closer to what we want to achieve. And to just show you this, I have another animation, which is the full state on the left and the accumulated time average on the right. And if we run it in time, we at the beginning see some signal of the fast waves, but if we run it for more and more in time, we will actually converge against this stationary geostrophic component. Okay, so this is just the boundary condition of the optimal balance, but we want to know how does the modified optimal balance actually perform in comparison with the original method where we use spectral analysis. And we did this for a whole lot of different dynamical regimes. Here, for example, for a Rossby number of 0.5, and we have the diagnosed imbalance versus the time averaging period, where a smaller diagnosed imbalance means that the method is working better. And we see that for a longer and longer time averaging period, the diagnosed imbalance is getting smaller and smaller and smaller until it eventually converges. And if we now plot the result with the original method, which is that line here, we see that it actually converged to it, which is pretty nice. That means we can just make the time average longer and longer and longer and actually get to the original method. We can also do it for a small other Rossby number, and we see the same thing again. They always converge. So now let's go to a little summary again. We learned that the time averaging method is converging against the original method, and that we can in theory apply them to really realistic ocean models. So we actually also did, just show you the result of the linear shallow water model, but we also did it in a primitive equation model or in more complex models, and it's also working there. The only problem is that we didn't yet find a way to deal with beta not equal 0. So this is the next step. And I think we're here at the end of our talk. Thank you for listening.